What's up, Cal Gang? Welcome back to some physics. So what do we have here? So we're given a block that's being compressed against a spring, and it's getting compressed 0.2 meters. Then the block is going to get let go, and it's going to travel 1 meter before it comes to rest, and it's going to lose all that energy due to friction. And our goal is to find that mu sub k, the coefficient of kinetic friction that the block and the table experience. So kind of complicated, right? We're not given a lot of information. It looks like almost too little information, but actually there's one formula that's going to help us out, and that's going to be the work energy formula. So I already made a mistake, right? So the work non-conservative is equal to the change in energy. So this is the golden formula in physics, right? In my opinion, of physics 1. And how do we use it? Well, let's look at each part. So non-conservative work, that's basically us putting energy into the system or taking energy out of the system. So the energies in the system, that's going to be your change in energy. Well, we have the spring energy, right? So compressing a spring gives us energy, because if we let go, it's going to give us a velocity. So we're starting with spring energy, right? We're being compressed, so we have a spring energy. And then we have a kinetic energy, right? We're going to gain velocity, and we're going to come to the rest. We're not changing heights, and the gravitational potential energy. So first of all, work not conservative, right? We said that what's taking energy out of our system? It's going to be friction, right? We know that there's going to be this friction coefficient, so there's going to be friction in our system. So we can relate this to the force done by friction times distance, right? Because work is equal to force times distance, technically times cosine of theta, but the angle between the movement and the normal force, or the friction force, is going to be 180. So we can actually just go ahead and do cosine of 180, right? Because friction, if we're to draw a force body diagram, and that's actually a good idea. Let's start out with a force body diagram. We have force of gravity, we have normal force, and we have the coefficient, or we have the force of friction. And so our motion, right, our distance, you could say, is this direction. And so the angle between the force of friction and distance is 180. So that's what this 180 is. And of course 180 is -1, so we'll make sure to account for that. So then now we're at our changes of energy. So this is the point where we're going to add up all of the energies that we think are in our system. So first of all, energy could be, right, the gravitational, or not the gravitational, right? We don't change height, but the spring or potential energy. So the spring is going to start with the potential energy, and it's going to lose that energy as we convert it to kinetic energy. So let's add delta K. So this is what we have now. So let's go ahead and convert this cosine of that to -1. So it's going to be negative force of friction times distance. And so what is this? So this is going to be U spring final minus U spring initial plus K final minus K initial. So those are what delta is. It's final minus initial. So let's go through these and see if any of them cancel, right? Some of them might be equal to 0. So our final spring energy, what does that mean? So final spring energy is basically, we're looking at this is initial, right? And this is final. So initially, we're compressed against the spring, so we have energy in the spring initially. However, once we get to this point where we're at rest, that spring is not in the system anymore. It's not having any effect on our block. So we have no final spring energy. However, like I just said, we have spring initial energy, so that's going to be minus spring initial. Now finally, we're ending, like we're looking at this as our final position, we have no velocity. If we have no velocity, we have no kinetic energy. Now what's weird is that at the beginning, right, this is initial, we also have no energy, right? Or no kinetic energy, right? We're starting at 0 velocity. And if we have 0 velocity, then we have no kinetic energy. So technically, from position 1 to position 2, even though it has a velocity, we don't care about it because it starts at 0 and it ends at 0. So what our system now says is that negative force due to friction times distance is equal to negative potential of the spring. And so what is this saying? Well, this is saying that all of the energy of our system, right? All of this spring energy that's held at the initial is going to be taken out of the system by friction, by the work done by friction. All right, so we're here, we can get rid of the negative signs, and let's expand this equation a little bit further. So force of friction, that's going to be mu sub k times normal, right? That's the equation for force of friction, and we're going to multiply that by distance. Then spring energy is 1/2 k delta x squared. So k is the spring constant, delta x is the compression. So what are we solving for? We're solving for mu sub k. So let's go ahead and divide by normal times distance. So we're going to get the muse of k is equal to k delta x squared divided by 2 normal times distance. All right, so we could probably just plug in numbers here. Also, let's look at our force body diagram because we don't know what normal force is. We know what everything else is. So if we look at this, we can take some of the forces in the y, and we know it's equal to 0 because we're not going up or below the ground, right? We're not accelerating up or down. And so what do we have? Well, we have normal minus force of gravity. So you go here, you get normal is equal to force of gravity. And of course, force of gravity is a constant mass times gravity. So we can plug that in here. So we're going to get the muse of k is equal to k delta x squared over 2 mass gravity distance. And so finally, let's just plug in all of the numbers we have. So k is our spring constant, 100 newton meters. Delta x is the compression of the spring. We know we compress 0.20 meters, so make sure to square that. Then the mass of our block is 0.5 kilograms. Gravity is 9.81. And distance, that's how far we travel. So that's going to be 1 meter, right? We travel 1 meter before stopping. And you solve for this, you get that the coefficient of kinetic friction is 0.41. And that's our final answer. So thanks for watching. Hopefully this helped you out. If you need any more practice with your work energy theorem, feel free to check out my channel. I've got a whole lot of playlists on that, a whole lot of videos on that. And I'll see you in the next video. Thanks for watching. Peace.